Here's a brief outline of what I will discuss today. We'll start with a look at stationary phase selection, uh, particle size selection, pore size considerations, and column and length ID considerations. Let's get right into stationary phase selection. These are some of the current trends in LC. In the center, we can see that we have increasingly complex and polar analytes. In order to tackle this, C18 remains the workhorse phase, and reverse phase separations still dominate. However, there has been an emergence of high aqueous phases as well as helic phases for reliable alternatives to alkyl phases for the separation and analysis of polar compounds. Speed of analysis or reducing runtime without compromising column life is another trend that we see. And finally, we see a number of alternative selectivities that look beyond the workhorse C18 for difficult separations and for fast method development and other features that are available by utilizing alternative phases. Let's focus on, this presentation will focus on reverse phase HPLC chromatography. Within reverse phase HPLC, there are various interactions that are possible. When we look at a C18 or an ODS column, the main interaction is hydrophobic or van der Waals interaction or dispersive interaction. However, there could be dipole-dipole interactions depending on the analytes and the stationary phase selected, as well as pi-pi electron interactions. And finally, there can be ionic interactions. In many situations, an analyte will experience some or all of these interactions in combination. So what is one of our chief selection criteria for looking at selecting a stationary phase? Well, one of the key breakdowns is by molecular weight. If your analytes and the compounds that you're looking to chromatograph are less than 5,000 molecular weight, then we have a whole set of criteria depending if it's water soluble, organic soluble, or chiral. If you have molecules that are predominantly water soluble, then again, reverse phase is one of the chief separation mechanisms that you would utilize. And again, in this category, C18 dominates. If your analytes are primarily organic soluble, again, there are a number of other techniques that are available, but reverse phase chromatography, again, is your chief focus. And again, there are many stationary phases, but chiefly amongst them would be the C18 or the ODS phases. Finally, if your molecular weight is less than 5,000, you may have a chiral molecule to separate, and we will not address that today, but there are special stationary phases for chiral separations. Now, if your molecular weight is greater than 5,000, let's say it's a large polypeptide or a protein or an oligonucleotide, then again, you have a similar criteria where you have a water-soluble analyte. And again, these would be primarily analyzed or separated by reverse phase chromatography. You can have an organic soluble, let's say a large organic polymer. Again, reverse phase might be useful, but again, there is a non-aqueous size exclusion for these rather large organic polymers. Again, today we will not be addressing any type of size exclusion chromatography. One of the key features, again, that when looking at C18, and C18 is the workhorse column, the go-to column for reverse phase separations. And in this graph, we could see a number of commercially available C18 columns from various suppliers. One of the chief criteria when looking at the performance of a particular C18 column is its solanol activity. In other words, is it able to interact with basic or amine containing compounds and producing an excellent or good peak shape? And we could see an example here where we're using pyridine as a test probe to look at the silanol activity. And in this case, this epic C18 column produces a very sharp and symmetrical peak. However, some of the other columns, columns A and column B, have somewhat of a tail, and they are exhibiting some increased silanol activity. So this is one of the key features when looking at C18 columns and choosing a C18 column, particularly for the analysis of amine-containing compounds. It's important that we understand what the silanol activity would be. Now, one of the difficulties in using conventional C8 or the workhorse C18 columns is if we utilize a stationary phase with a high aqueous component, another mobile phase with a high aqueous component, more than 95% aqueous. And we would use that particularly for the retention of polar compounds. But if we use a conventional, heavily well-encapped, let's say C8 or C18, we'll experience a low retention for polar compounds, poor retention time reproducibility, poor peak shape, and poor reproducibility under gradient conditions. There are several reasons why the NCAP C8 and C18 fail to perform adequately under highly aqueous mobile phases. It is chiefly believed that there is a hydrocarbon chain association and a water exclusion from the silica pores. The pores are very important for the interaction of the analyte and the stationary phase, as most of the bonded stationary phase resides in the pores of the column. And this is an idealized graph of a pore. And we can see in the upper portion, the analytes are properly retained. The mobile phase can be seen entering this idealized pore structure. However, if the analytes or the mobile phase can't enter the pore structure at the normal operating pressure of the column, the analytes are partially retained or even unretained. In order to overcome this, we have developed an ether length stationary phase, which makes the stationary phase. It has a C18 chain, but at the base of the chain is an ether linkage. This ether linkage is polar enough to allow water, or the mobile phase, which is primarily consisting of water, to enter the pore structure at the normal operating pressure. So utilizing this type of C18 phase, we can have an analysis of organic acids, low molecular weight organic acids. And in this case, we performed a separation of 11 organic acids utilizing a mobile phase which just contains 50 millimolar phosphoric acid, and the rest of the mobile phase is 100% water. So we can see we get excellent retention and we get excellent reproducibility of the separation time after time using this ether-linked C18 stationary phase. The ether-linked stationary phase, however, can perform very similar separations to the heavily encapped C18 phase and can be used with organic modifiers. In this case, we are looking at the separation of caffeine in several brewed beverages, including tea, coffee, and soft drinks. And in this case, we're using mobile phases that contain 20% acetonitrile. But again, we could see in this diagram that the C18 is the center and the workhorse. However, there are many separations in which the C18 fails to provide adequate or even poor separation of many analytes. We could see a comparison of two chromatograms on the right side, a separation of 4 components. These are nitro-aromatic compounds. On the C18 fails to provide separation for 2 of the 4 compounds. So we only see 3 chromatographic peaks. However, if we utilize a PFP or a pentafluorophenyl stationary phase, we could get baseline separation of all four of the nitroaromatic compounds. And also, we could see in the center that we have the C18, and we could see that the various stationary phases are radiating out from the C18. These are the selective or alternative chemistries that have been developed over the years to utilize retention mechanisms beyond the hydrophobic mechanism of the C18. So why do we want to do this? Well, in some cases, we want to provide phases that have an orthogonal separation to the alkyl phases, the C8 and the ODS or C18 phases. In some cases, we need to improve sample loading for preparative separations. We'd like to resolve, in many cases, complex mixtures of chemicals with closely related structures, such as isomers. And we may want to shorten the retention while maintaining resolution for particularly for lipophilic compound. I'd like to now look at some of the alternative phases. In particular, I'd like to look at the fluorinated stationary phases. Again, I had mentioned pentafluorophenyl stationary phase earlier, and we can see a structure of a bonded pentafluorophenyl phase to a silica in the lower left-hand corner. These pentafluorophenyl stationary phases are useful for the separation and retention of aromatic compounds through pi-pi interactions and charge transfer. Compounds with polarizable electrons such as alkenes and conjugated systems, as well as aromatic halogenated compounds. They can also participate in a fluorophilic retention mechanism for fluorinated compounds. And this is one application where a pentafluorophenyl would be useful over the ODS or the C18 workhorse phase. For the ODS phase, we have a minor impurity that's on the tail of a major component. The quantitation of this minor impurity can be very difficult on the tail of a major component, as we don't quite know where to draw a baseline for an accurate quantitative result. However, if we utilize the pentafluorophenyl stationary phase, in many cases we can get a reversal of elution order. So we can now take the minor component and bring that to the leading edge of the major component, and we can get a baseline separation with an excellent peak shape for the minor component, and we can easily draw a baseline to get more reproducible quantitative results. Another situation where the pentafluorophenyl is useful is complex natural product analysis. In this case, this stationary phase was utilized to separate Taxol, which is an anti-cancer drug isolated originally from a natural product, the bark of the Pacific yew tree. Being a natural product, there are a number of isomers that are associated with Taxol. These all have minor structural variations, and a typical C18 phase has a difficult time in generating baseline separation for these very similar structurally compounds. But with the case of the pentafluorophenyl, we could get baseline separations, or at least some separations, between this complex mixture of the natural products. In this case, we have separated 14 Taxol-related compounds, again, from the bark of the Pacific yew tree. Another area where the pentafluorophenyl phase or fluorinated phases are useful is in the case of perfluorinated octyl. In this case, we do not have an aromatic group. We have an alkyl chain to which the hydrogens have been substituted by fluorine groups. This has proven to be useful for the separation and retention of lipophilic compounds, as it's less hydrophobic than either C8 or C18. And it does provide for significant contribution to the fluorophilic retention mechanism. And this is just one example. We could see vitamin K in the lower, the structure of vitamin K in the lower left-hand portion of the slide. This is a very hydrophobic molecule. It has three of the hydrophobic chains at the conjugated system. So on a C18 column, this really retains very highly, and in some cases it's very difficult to separate from other hydrophobic impurities that are contained in the sample. And we could see that we're looking at vitamin K. We have the standard vitamin K on the left, and then we actually are able to determine vitamin K in fresh spinach. And this product is, this chromatogram was developed just by grinding up spinach, extracting it with an organic solvent, and then injecting that organic solvent directly into the chromatograph. With the C18 column, it would be hard to isolate and determine the vitamin K because of its hydrophobic nature and the hydrophobic nature of other compounds within the sample. However, with this perfluorinated octyl stationary phase, you're able to get a reasonable retention and separation of vitamin K. There are other alternative phases, and many of these are based on phenyl structures. And here is an array of these phenyl alternative stationary phases, all the way from a regular phenyl compound bonded to silica, a phenyl hexyl bonded to silica, a diphenyl, a biphenyl, and a naphthyl. Again, they can have the retention time, retention of aromatic compounds through pi-pi interactions. The compounds where polarizable electrons, such as alkenes and conjugated systems, work well with these types of stationary phases. And this is just a couple chromatographic examples of biphenyl and naphthyl stationary phase. In the lower left-hand portion is a separation of cannabinoids utilizing a naphthyl-based stationary phase. On the right-hand portion of the slide, we can see the separation of aromatic compounds on a biphenyl stationary phase. Both the biphenyl and the naphthyl have planar molecules that enable high-density bonding. This provides for the strongest pi-pi non-fluorinated phenyl phases available. Now that we've looked at the stationary phase and given some input into looking at various alternative stationary phases as well as C18, the next point that we should review is choosing particle sizes for that particular stationary phase. In this slide, we could see that for preparative chromatography, we would use rather large particle sizes. They would range anywhere from 5 micron to 20 micron. For standard HPLC, we could utilize particle sizes from 3 micron to 10 micron. And for ultra-high performance or ultra-high pressure HPLC, it is generally preferred that we use 1.8 micron particles. Now, one thing that's very important to note is that your choice in particle size is related to the quality of your HPLC. In this case, we can see that we're comparing two different chromatograms, one with a larger dead volume or internal volume of 22 microliters, compared to a system that's optimized at 12 microliters. You can see that we get baseline separation of all our components with the optimized system. But we fail to get, when we get broader peaks in the non-optimized system. So it's important that you match your HPLC to the particle sizes that you desire to utilize or need to utilize. And again, smaller particles equal higher efficiency, which equals better resolution. So we could see a comparison of a 1.8 micron particle versus a 5 micron particle, and we could see how much sharper the 1.8 micron peak is versus the 5 micron. We can also see that if we are trying to resolve a pair of compounds using the 1.8 versus a 5 micron, the 1.8 is able to get baseline resolution of these two compounds, where the 5 micron does not. And again, if we need to quantitate, it's better to have a baseline separation than a partial separation. What are some of the reasons that we find that smaller particles provide for a higher or more efficient separation? Well, there's an equation referred to as the Van Deemter equation, and it refers to broadening, factors that broaden a chromatographic peak. There are three distinct parts of the Van Deemter equation. The A term, or the eddy diffusion term, or the multipath effect. We have the B term, which is the molecular diffusion, and that's the actual diffusion within the stationary phase. And then the C term, which is the mass transfer from the stationary phase to the mobile phase. The mu in this case is the linear velocity, and we are measuring the height equivalent to a theoretical plate, or the HETP, and that's the H. The lower the HETP, the sharper the peak. So how does flow rate relate to particle size? We have drawn here three Van Deemter plots in which we measure the HETP versus the mobile phase linear velocity. And we could see that the narrowest peaks are shown with the 1.8 micron particle size, and the biggest peaks in this case, or the widest peaks, would be shown by the 5 micron particle. In addition, we're able to maintain the chromatographic peak HETP over a wider range using the smaller particle, a wider range of flow rates. So again, let's go back to the Van Deemter equation. So our H, our height equivalent to a theoretical plate, is again based on three parameters related to mobile phase velocity. The A term is the eddy diffusion term, or the multipath effect. The A term decreases with particle sizes. As particle sizes decrease, the A term decreases, so it contributes less to the height equivalent to a theoretical plate. If we look at the B term, that's the molecular diffusion, or diffusion within the mobile phase of the solute. This term is not affected by particle size and usually becomes negligible at a significantly high flow rate. The mass transfer term, however, is affected by particle size, and again, C decreases with decreasing particle size. And this is the mass transfer, the analyte's ability to go in and out of the stationary phase into the mobile phase. And again, if we reduce the C term, we will end up with a smaller height equivalent to a theoretical plate, which translates into a sharper chromatographic peak. So here's a real-world example comparing two different particle sizes. In the upper chromatograms, we could see a 3 micron particle, again, run at 1 mil a minute. We get almost 19,000 plates for our theoretical plates for our separation, and this represented by very sharp peaks. If we now increase the flow to 1.5 mils a minute, we do lose some sharpness, but it's a 9% loss. Again, these are 3 micron particles. However, if we look at the chromatograms in the lower portion of the slide, we can see that these are 5 micron particles. And again, at 1 mil a minute, we do get less plates, or a bit of a broader peak than we do on the 3 micron particles. However, what we see is a real difference is if we increase our flow rate to 1.5 mils a minute, we see we have a 15% loss in efficiency, as opposed to the 9% loss that we see with the 3 micron particles. This is even more dramatic when we go from a 5 micron particle to a 1.8 micron particle. And in this case, we've adjusted everything so that we have reduced our analysis time from 27 minutes for the 5 micron particle, and we're able to maintain the same resolution with the 1.8 micron particle in less than 3 minutes. So again, influence of particle size. The advantages of smaller particles is we have reduced diffusion, increased efficiency and resolution with the same runtime, higher sensitivity, narrower, taller peaks, higher peak capacity. We could fit in more peaks into per unit time because the peaks are sharper, and we have a reduced influence on flow on the separation efficiency. However, there are some disadvantages. We do have increased operating back pressure. The HPLC instrument must be matched to the higher or smaller particles, and it also puts a greater demand on the column hardware to perform or to utilize the performance gains with from the smaller particle sizes. Next parameter we'll study that's part of column selection will be looking at pore size. And this is just an idealized diagram of what the pores would be on, let's say, a silica particle. They enter the actual particle. And again, we could see the bonded phase in yellow goes into the pore. And it turns out most of the bonded phase resides in the pores. So what is the influence of pore size on a given separation? First of all, surface area is inversely proportional to pore size. So generally, higher surface area silica will have smaller pores. Most interactions occur between the analytes and the stationary phase within the internal pore structure. If pores are too small, large molecules cannot access the stationary phase because, again, most of the stationary phase resides in the pores. If the pores are too large, the particle can become fragile. In addition, the interaction, particularly for a low molecular weight molecule, can be very low because, again, surface area is inversely proportional to pore size. So for small pore particles, let's say pore sizes between 60 and 150, pore diameter is not usually in consideration. However, 60 angstrom pores in some cases can provide unique separation characteristics. Where pore size is very important is larger molecules greater than 5,000 molecular weight. These molecules are too large to enter the pores of, let's say, 120 angstrom particle, but they can enter the pores of a 300 or 400 angstrom particle. So very important to try to match the pore size of the particles that you're utilizing to the analytes that you're interested in retaining and separating and analyzing. So in the case of proteins or a very large polypeptides or oligonucleotides, it may be beneficial to go up to 300 angstrom and larger pore sizes to accommodate these high molecular weight molecules. The final two important parameters to look at when selecting columns are the actual column dimensions. And this would be the ID and the length of the column itself. We could first look at the length and the influence of column length. In this case, we've used 5 micron particles. They're all EPIC C18, and we just vary the column length on a mixture of 5 components. We could see in the 100 millimeter column, or the column pictured on the top, we get plates on the final compound of the mixture of 9,300 plates. The resolution between peaks 4 and 5 is 7.3. However, if we take the same mixture and now we utilize a 150 millimeter column, we can see we gain more plates, almost 14,000 plates, and we increase our resolution on components 4 and 5 from 7.3 to 9.0. Finally, if we go all the way to 250 millimeters, we end up with 20,000 plates, and we've further increased our resolution to 10.9. However, it should be noted that we don't see dramatic changes in either plate counts or resolution as we increase our column lengths. We see an incremental change in plates and an incremental change in resolution. So in many cases, it is more desirable to change particle size. That'll give us a greater change in our plates and our resolution than column length. And ultimately, it may be necessary to use an alternative stationary phase to really improve the resolution for certain components. So, in terms of advantages increasing column length, is you increase retention, you get better separation, increase efficiency and resolution. The disadvantages are significant, including longer analysis time, greater solvent consumption, increased back pressure, greater cost for the column, and lower overall column efficiency in terms of plates per meter. Again, as I previously mentioned, a better approach would be decreased particle size and also to think about decreasing column ID. Again, another way of doing this would be actually to look at alternative stationary phases to improve the resolution and maybe even improve the shorten the analysis time for the separation. So now let's look at the effects of column ID. So I've broken it up into two categories. Larger diameter columns, these are equal to or greater than 4 millimeters internal diameter. There are some advantages to using these larger ID columns, including greater sample loading capacity. They can utilize larger sample injection volumes and can be used, very importantly, on standard HPLC instruments. You don't need the latest state-of-the-art ultra-high resolution instrument to utilize these 4 millimeter ID columns and larger. The disadvantage of the larger ID columns is the greater solvent consumption, lower sensitivity, and they're not directly compatible with LCMS. The other category of column diameters to consider would be smaller diameter columns. And these are columns between 2 and 3 millimeter ID. There are a number of advantages of the smaller ID columns, including greener because of the lower flow rate requirements, less radial dispersion, in other words, we enhance detector sensitivity, readily compatible with LCMS operating conditions. Smaller injection volumes are required, so if you're sample limited, these smaller ID columns can be very useful. The disadvantages of the smaller column ID include lower sample capacity and the requirement that the HPLC instrument be optimized for the narrow bore column. So if you have an older instrument, you might not be able to realize the benefits of the narrow bore columns. One of the key features of the narrow bore columns is increased sample sensitivity. And we could see an example here of a chromatogram, one with a narrow bore column, a 2.1 millimeter column, in which we are able to get 5 times the sensitivity than a conventional 4.6 millimeter ID column. And then again, this is a UV detector. So again, by utilizing the narrower bore column, we're able to get much higher sensitivity. Another point is that you end up with a lower solvent consumption. So if we look at the solvent consumed in 5 20-minute runs, if you have a standard 4.6 millimeter column, you will consume 100 mils of solvents for 5 20-minute runs. If we now reduce that internal diameter from 4.6 to 3 millimeters, we now reduce the solvent consumption to 40 mils total, which is a 60% savings. If we further reduce the column internal diameter to 2.1, we now reduce the total solvent consumption for 5 20-minute runs to 20 mils total. And we now experience an 80% solvent reduction or savings in solvent consumed by utilizing the 2.1 millimeter ID column. So what are the typical characteristics of various column IDs. So again, if we look at the 2.1 or the narrow bore column, its ideal flow rate range is from 0.2 to 0.5 mils a minute. Its typical sample capacity is 100 to 500 micrograms. And again, as we showed on the last previous several slides, its relative mass sensitivity is greater than 5 times when compared to the conventional 4.6. So even by going to the 3 millimeter column, we have an ideal flow rate range of 0.4 to 0.8 mils a minute. We have a typical sample capacity of 200 to 1,000 micrograms, and we do have some improvement in a relative mass sensitivity of 2.4. The 4.6 or the conventional columns, or typically used columns, have a flow rate range anywhere from 1 to 3 mils a minute, have a sample loading capacity of 1 to 5, and do not experience any relative sensitivity when compared to the narrow bore columns. So in summary, it is clear that the C18 still remains the workhorse stationary phase for HPLC. However, alternate selectivities are useful for rapid method development, as well as improving resolution, showing orthogonality, and other factors that are useful with the alternative phase chemistries. Smaller particles yield higher efficiency separations. However, the HPLC must be engineered to utilize these smaller particles. Pore size is very important for large molecule analysis, but is not a primary consideration for small molecules. Longer columns provide higher resolution. However, it is generally better to reduce particle size, column ID, or to look at alternative stationary phases as a way of improving separations or improving resolution. Again, the longer columns can do this, but there is a penalty, including greater solvent consumption, higher column cost. Finally, smaller ID columns allow for greening methods through the reduction of or the saving of solvents used for the analysis. However, the HPLC instrument must be optimized to utilize these smaller column IDs. And with that, I thank you for your attention.